I will find out after class. You're going to solve it for me. All right, guys, everybody calm down. Your laptops shut, all the good stuff. Muno, your laptop. Thank you. Lady there, you neither have your name tag out nor your laptop shut. Wait, somebody's playing out my video from last class. That sounds like my voice. All right. Okay, let's start. It's 12:30. The class is awfully sparse today, and the few people who did come seem to have left already. So it's we're preparing for spring break. Spring break comes early. It comes on Thursday. It comes earlier every year. One day you'll have spring break in January. Anyways, so here's where we were. The story so far was that iterated structures are good for analyzing time series data with short duration dependence on the past. So if, for example, making a prediction today could benefit from knowing what happened in the past 3 days, you'd have a structure of this kind. This is your convolutional neural network. But if you want something where the model must analyze everything going back into the infinite past, you want recurrent structures of this kind, right? Now, recurrent structures, I explained recurrent structures as models that are good for modeling time series. But it turns out that they can actually be used in other places as well to good benefit. So let's consider a simple problem. Let's say I want to add two numbers. I want to learn a network. So I give the network examples of pairs of numbers and the sum. And the network must learn from these collections that the operation it's performing is addition, right? So in that case, the network was going to look something of this kind, which is I have two inputs. Again, these are binary for my example. And then I have a single output, which is the sum. Now, if I decide to have only one hidden layer, how large is this network going to be? Anyone? Ritian? Pardon me? The problem is to train a network to add two binary numbers. And now, so the way the network is set up, you're giving it both the numbers, and then it must produce the output. If I want this network to have only one hidden layer, and I want it to accurately learn the task of addition of binary numbers, how large must that hidden layer be? Pardon me? 1 neuron. 1 neuron? Is it going to be able to add every 8 neurons. 8? Where did you get 8? Look at the string, right? So number of bits plus number of bits will add and the final bit. Really, if I just have one hidden layer, this is an XOR problem, is it not? Addition is XOR. How large must the network be for XOR? Pardon me? It's exponential in the size of the input, correct? So this network would have to be exponential. Now you could sort of try to do something clever, make it deep. If the network is deep, it doesn't have to be exponential anymore. And you can still train the network, but then here's the constraint. If I trained a network to add two n-bit numbers, and it learns to generate an n plus 1 bit number, now if I want to add two n plus 1 bit numbers, can I use this network? No. No, because it's trained for specialized to n-bit numbers. Second. Third, even if I've got all the right architecture and it's not exponential in size, how much training data must I provide for it to learn the concept of addition? Exponentially, you have to basically give it every single example because it's going to be memorizing, right? So you would need 2 raised to 2n training instances for it to learn everything. But then if I recast it as a recurrent network, that's all I really need, right? One little unit. And it's going to take in 3 bits, 1 bit each from each of the 2 numbers and a carry bit. It's going to produce 2 outputs, which is the output bit and the carry bit for the next input. That's it. And so here, how many inputs do I need to learn this network? There are 8 combinations of 3 inputs. And so with just 8 inputs, we'll learn the network. So, and how big is this network going to be? Tiny, 3 neurons or 4 neurons, right? So you can see, so do you see how, Adrita, you're looking here, you're either falling asleep or you didn't make that clear? So do you see what happened over here? I took a standard problem and which is something that you'd consider the processing of static sets of numbers. But then when I recast it using a recurrent framework, the size of the network shrank tremendously and the amount of training data required collapsed to nothing. So can you give me another example of this kind? Advait? Anybody? Thomas? No? Parity, right? So here's the thing. What is the parity? The parity bit, the problem of computing parity is the problem of computing the number of ones and zeros. If it's even, the output is 0. If the number of ones is odd, the output is 1. Now, if I want to learn the concept of parity, I can train a network for it. And if the network has only one hidden layer, how many neurons will I need in the hidden layer? Parity is also an XOR problem, is it not? So what would it be? Exponential in the size of the input. Suppose I decide to have many layers. I allow it to be deep. In that case, what would the size be? It's going to be linear. We saw that you can do it in 2n. Even so, how much data would I have to provide it to learn to compute the parity correctly for every possible input?
Okay, its number of bits 2 to the power 2.
So you're going to have to basically give it an exponential number of bits, training instances for it to learn the concept of parity, right?
So it's a memorizer.
Because these are basically random patterns. So you will be memorizing. It's always the worst case. On the other hand, if I do it with a recurrent network, this is what it looks like. I'm going to have one unit, and I have the previous parity. If the input is 0, the output remains as a 1. The output is always going to be the same as the previous output if the input is 0, and it's going to be flipped if the input is 1. That's a very simple thing. How many training instances will I need to learn this? 4, right? Or one sequence of 4, a single sequence of 4 bits will learn this. And here's the other thing. This network, if I train this network to compute the parity correctly for n-bit numbers, I cannot use it for n plus 1 bit numbers. This guy is arbitrarily sized. So you can, the point is this. Okay, 5 seconds, guys. Yeah.
Aren't like the problems that you mentioned, aren't they just better modeled with logic gates? Like why would you want to model it as an error problem in the first place?
A logic gate is an instance of a threshold unit, right? So I'm just doing this with networks. I'm giving you examples, that's all. But anyway, time's up. Marlies, I promised you, what is the answer to the first question? And the second? Thank you. So you're off the hook for the rest of the day. So clearly, some prediction and classification problems that require very large MLPs and a large amount of training data can be solved using small recurrent nets that only require small amounts of training data. Recurrence can make things easier. And similarly, some problems that require large, complicated convolutional networks can be made very simple by using recurrence. So far so good. Now here's the rest of the story so far. We said that these networks can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. It's not, the sum of the errors over every output. It's the error over the two sequences. And now, this is a recurrent model, right? Somebody asked me a question in the last class. How do you know it's not going to blow up? So let's start off with this one. This is not a recurrent model. This is just your standard convolutional network. Now, assuming that all the parameters of the network are bounded, if the input is bounded, can the output ever blow up? Can it go to infinity? Can it tend to infinity?
No.
Why not?
Because it only takes in finite.
You're processing a finite number of values, right? Unless the functions or the activations themselves blow off to infinity for finite values, which they don't, then whenever you're processing a finite set of values and the slope of the function is bounded, the slope of every activation is bounded, and if all of your weights are bounded, the output must be bounded, right? So in other words, for bounded inputs, this is the output here is also bounded. This is what is called BIBO, bounded input, bounded output, stable. This is a BIBO stable network. Make sense, right? Questions? No. Now, this is a highly desirable characteristic. You don't want your network to go off and blow up. What about this guy? Is this going to be BIBO? Yutian?
No.
Why not?
Because it's an infinite response system.
It's an infinite response system. So what are the conditions under which this is going to be stable?
If we can clip the values.
You can?
The values.
Okay, good question, good answer. If I clip the values, what does it mean? It's the same as blowing up because you basically saturated the output, right? This system has the capacity to become uninformative and useless. So that's to answer your question. If the input and output, if I have saturating activations, then it's going to saturate, and then once it saturates, there's no further information coming out of the system. So let's try to figure out when this thing can blow up and what its behavior is like. Now, here is the characteristic of a recurrent system. The key behavior we wanted was that we wanted it to remember things for a long time. Something that happens today could potentially affect the behavior of the stock market next year. So you want the event that happened today to be held in memory for 365 days. You want things to be held in memory until they're no longer relevant. Let's see if this does that, right? Now, in order to analyze this, the actual recurrence only occurs in the hidden layer, the recurrent layer. The rest of them don't have any accumulation going on. So to understand how this behaves, we have to look only at the recurrent layer. Let's look at this one. Now, it turns out that analyzing the recurrent layer is really painful because you have nonlinear activations and nonlinear things going on. So we're going to go back to our old trick. Here's a problem that we cannot analyze. So we will go and analyze a problem that we can analyze and then try to find the relationship between the two, right? The old streetlight effect. So I'm going to analyze a linear system. By linear system, I mean that my activations in the green boxes are linear. There is no, I'm just computing an affine function at each stage. And then having computed an affine function, I'm not doing any other processing. This is just an identity transform. Each box, the activation in each box is an identity transform, okay? So if I look at that, each hidden unit simply produces the affine value itself as its output. The affine value at any time is the hidden unit's recurrent weights. WH represent the recurrent weights. The recurrent weights times HT minus 1 plus the bias. Let's ignore the bias for the moment, okay? So if I write it out, this is what it is, right? I'm going to have, are there chalks here? Why do chalks disappear? So I have a HT, is it? HT equals W times HT minus 1 plus, I'll call this WH, WX times XT. So you have the connection going up from the bottom, and you have the connection, the recurrent connection coming up the side. This is the recurrent weight, and this is the current weight going up from the input. But then I can write HT minus 1 make equals WH HT minus 2 plus WX XT minus 1, right? So let me plug this in. If I plug that in, what do I get? What is HT? It's going to be WH squared times HT minus 2, right? Plus WH WX times XT minus 1 plus WX XT. So we've written the current output in terms of things that the recurrent value 2 time steps ago, right? But then I can write WHT minus 2 is going to be WH HT minus 3 plus WX X T minus 2, right? So if I plug this in, what's it going to look like? HT equals WH cubed HT minus 3 plus WX squared WX XT minus 2 plus W HWX XT minus 1 plus WX XT. Can we generalize this? Can you generalize it? You've seen the pattern, right? What do you think the general pattern is going to look like? So if I expand it out, this is going to be, if I go back k steps, it's going to be WHK HT minus k plus WH raised to k minus 1 WX X T minus k, right? Plus WH raised to k minus 2 WX XT minus k minus 1 and so on, all the way till you get WX XK. That's what it's going to look like, right? So that's your second loop, and that's the general WH raised to k plus 1. I got something off, but you get the idea of how this works. Okay. Now, if I want to analyze this, this is entirely linear, right? What is that first guy, that second term? That second term over here is the response of the system. If you had no h minus 1, if h minus 1 was 0, then there's no prior input, right? And so this is the response of the system if you had a single input x0 at time 0 and no further inputs, right? So I can write that. So let me write that response to an input at time 0. The response at time k to an input at time 0. I'm going to write this as hk x0. So hk means this is the response at time k. x0 is the time input at time 0. Similarly, the next one is hk, the response at time k to an input at time 1. This is just, notation. Now here is the thing. If I want to analyze this, so this is linear, so I can pull the x0 out, assuming all the inputs are scalar. So I can just write this as x0 times hk, which is the response at time k to a unit input at time 0, right? Because it's linear, and so x0 comes out. Now, and the initial, and h minus 1, I can just think of it as an initial condition. Let's assume it's 0, okay. I can write the same thing in vector format. Now, this is scalar. In vector format, you're going to have the same thing, except that the 1 is going to be maybe a vector of 1s, or right? And the h's are going to be, or hk of 1 is going to be a matrix, right? Now, so to analyze the response to a single input at time 0, but here's the thing. The response at time k is your initial response, initial input, which we will ignore, plus the response x0 times the response to a unit input at time 1, plus x1 times the response to a unit input at time 2, plus x2 times the response to a unit input at time 3, and so on. That making sense to everybody? Right. If this is going to blow up, this must have blown up because it's linear, right? You're always sort of working on something. If something has blown up, everything afterwards must blow up because you're working on things that have exploded, right? And so because of the recurrence. And so if the response at time to the input at time 1 has blown up, that is sufficient. I just need to check if the response to an input at time 1 has blown up, right? So I just need to focus on this one guy, that first term. Now let's consider what happens. Yeah.
What is the relation between 1, 0 and x0 again?
So I'm just saying that I can write x0 as x, the number times a unit vector, right? Or a unit value. So just a unit input, okay? Now let's consider the scalar case. So I have ht again. I have ht equals w ht minus 1. I'm going to assume that wx is just 1 or c times xt, right? So let's say I have just a single input, 1 at time 0 and nothing else, okay? So then what is h of 1? h0. That's simply going to be c, right? What is h of 1? All subsequent inputs are 0. So what is h of 1? C times w, correct? What is h of 2? C times w squared, right? What is h of t? C times w raised to t. What can you tell me about this? When will it blow up? When w is greater than 1. And if w is less than 1, what happens? It's just going to collapse to 0, right? That's basically what you have. Different values of w. For small values of w that are less than 1, it's going to just die. For values of w that are greater than 1, it's going to blow up. Only for w is it equals 1 is it going to hold whatever you want it to keep in memory. That making sense to everybody, right? So I can write the same thing for in vectors. This was for scalars. Now there's a lot of math on the screen, but here is, let me try to simplify it, so ignore what's on the screen, and maybe we can do it on the board. As always, I'm going to run out of time. You guys are incredibly patient. So I can take any matrix W and I can write it as U lambda U inverse. This is eigen decomposition, almost any matrix, unless it's one of those broken matrices, right? So the eigenvectors represent independent directions. If W is symmetric, they're orthogonal, but regardless, the eigenvectors represent independent directions, right? And so corresponding to every eigenvector Ui, there's going to be an eigenvalue lambda I. And so W times Ui equals lambda times Ui. This is the eigen relationship, correct? Now, because these eigenvectors represent independent directions, I can write any vector x as x equals some u1 times c1 plus, or let me call this a1, plus a2 times u2 plus a3 times u3, and so on. I can represent any vector in terms of the eigenvectors of my W matrix because they represent independent directions. That makes sense? Right. What happens if I multiply x with W? What is Wx? That's going to be a1 times wu1 plus a2 times wu2 plus a3 times wu3, and so on. Right? You with me? What is this term? What is that? Lambda 1, right? So this is going to be a1 times lambda 1 times u1 plus a2 times lambda 2 times u2 plus a3 times lambda 3 times u3, and so on. If I multiply this again by w, what will happen? I'm going to, if I multiply, so if I have w times wx, w squared x, which is w times wx, this is going to be a1 lambda 1 squared u1 plus a2 lambda 2 squared u2, and so on. This making sense? Okay. Or in general, w raised to t x equals a1 lambda 1 raised to t u1 plus a2 lambda 2 raised to t u2 and so on. Okay, so everybody with me? Now I can rewrite this. So without loss of generality, let's assume that lambda 1 is the largest of the eigenvalues. Okay, and so if lambda 1 is the largest of the eigenvalues, I can write this as lambda 1 raised to t times a1 times lambda 2 over lambda 1 raised to t u1. So actually this is, sorry, a1 times u1 plus lambda 2 a2 times lambda 2 over lambda 1 raised to t u2 plus a3 lambda 3 over lambda 1 raised to t u3 and so on. Right? Have I lost anybody? Does this make sense? Can I see some heads nodding? So it makes sense. Okay, what can you tell me about the behavior of this one? Teacher, is it making sense? Not very much. So, okay, finally an honest person. Where did I lose you? So basically, I just wrote this guy by taking lambda 1 t raised to t out as a common factor. So I have that lambda 1 raised to t out here, in which case I'm just going to get lambda I divided by lambda 1 raised to t, right? And what are these values? Are they equal to 1, greater than 1, or less than 1? Less than 1. What happens as t increases? They're all going to go to 0, right? In the limit, the only thing that you're going to have left is going to be a1 times lambda 1 raised to t times u1. The rest of them are going to disappear, correct? And so as t tends to infinity, this is simply going to become, this becomes a1 lambda 1 raised to t u1. That's it. That's all that remains. Yes?
Taking out lambda 1 transpose common.
That's not transpose, that's raised to t.
Raised to t, sorry, my bad. A common results in the lambda 2 by saying.
Because this second term is going to be lambda 2. I'm pulling out lambda 1, right? So it's going to be.
Why pulling only lambda 1 to the power to common?
I just pulled out the most the largest value. That's it.
Oh, okay.
I can pull out any value, right? I just pulled out the largest value. So this makes sure that all of the other multipliers are less than 1. Right? So what does this tell me about the behavior of this recursion? This recursion is only going to preserve the component with the largest eigenvalue, right? And furthermore, so the length of the hidden vector will expand or contract according to the tth power of the largest eigenvalue of the weights matrix. That's about it, of the recurrent weights matrix. And if this largest eigenvalue is greater than 1, what's going to happen to your hidden representation? It's going to, is it going to blow up? Is it going to stay flat? Is it going to die?
Greater than 1 it will go.
It's going to blow up if the largest eigenvalue is greater than 1. If the largest eigenvalue is less than 1,
Collapse.
it's going to collapse to 0, right? And so this is the kind of behavior you have. So I'm showing you in the figure to the right what happens when lambda max is 1.1. It just blows up. For lambda max is 1, it stays flat. To the left, I have two figures. There's a little bit of wiggling. Why is that? It's never going to be monotonic because your eigenvalues are often complex. And so you're going to get this complex wiggly kind of behavior, but nonetheless, it's going to fall off, and some of the behavior is going to depend. The early behavior depends on lambda 2, but when you go far enough out, the only thing that remains is lambda 1, right? So is this making sense to everybody? Yeah.
Why did you say when you pull out the largest one, all the others, do you think you said go to 0?
Because lambda 2 over lambda 1 is going to be less than 1.
Oh, I see, yeah.
Right? So something less than 1 raised to t goes to 0 really quickly, right? And so In linear systems, long-term behavior depends entirely on the eigenvalues of the recurrent weight matrix. If the largest eigenvalue is greater than 1, the system will blow up. If it's less than 1, the response will vanish very quickly. Complex eigenvalues can cause oscillatory response, but with the same overall trends. And the rate of blowing up or vanishing depends only on the largest eigenvalue, right? Yes, Firas.
I didn't get why complex eigenvalues are oscillated.
Oscillatory response because you have they occur in complex conjugate pairs. The sums of complex conjugate pairs are sines and cosines, right? That's why. Okay. Anyway, so this is when things are purely linear. But in your real system, your recurrent layer doesn't have linear activation. It has an activation function, right? How does it behave with activation functions? Let's take a look. So this is with sigmoids. So now I'm computing the affine value, but then I'm putting it through, I'd say, through a sigmoid activation. I have taken 3 examples. So in each figure has 5 bars. The 5 bars represent 5 different values of the bias B. There are 3 rows, and the 3 rows represent 3 different values of the weight W. So 1.1, 1.0, and 0.9. And there are 3 columns, and the 3 columns, this is all the response of the system to a single input at time 0 with no further input, okay? And so the 3 columns represent the response to inputs of minus 0.5, 0, and 0.5. So 3 different inputs, initial inputs, 3 different weights, and 5 different biases. What do you find? They basically look the same, right? The only difference is the difference in the bias. You have 5 different bars. If you look at the picture to the far right, this is what happens across time. After a very small number of steps, all that remains is information. Does it have information about the input? Towards the end of the plot, do any of these pictures have any information about what the input was? Is the input being remembered? What is being remembered? Just the bias. The only thing that was remaining in this network output was the bias. And it happened very quickly, 3 time steps with a sigmoid. And if I do it with a tan H activation function, you get very similar behavior, except that it takes a slightly longer to get to this point of no memory. So in recurrent neural networks, you almost always use tan H activation functions in the recurrent layer. Why? Because the tan H remembers things for slightly longer than a sigmoid. That's why you use tan H activations in the recurrent layer, okay? If I use ReLUs, what happens? You get the same kind of behavior. If the W is greater than 1, it's going to blow up. If the W is less than 1, it's going to die. And the manner in which it blows up depends a little bit on the bias. But at the end, the place where the network ends up after T time steps, if it's blowing up, I don't care. It's blown up, right? And if it's not blowing up, where it ends up is going to depend only on the parameters of the affine values. It doesn't depend on the input X, right? So these things don't really have very good memory. But this was for scalars, right? Let's do the same thing with vectors. Here, I have the same kind of recursion. H equals f of w times ht equals f of w times ht minus 1 plus some matrix C times xt plus a bias B, okay? So now, these are 5 different values of the bias. So in each case, I've given it an initial vector of all ones or an initial vector of all minus ones. So the upper ones is an initial vector of all ones. The bottom one is an initial vector of all minus ones. And the first column, of course, is 2 sigmoids. I'm changing the bias. The 5 different rows are different values of the bias. And what do we see again? After very few time steps, all that remains is information about the bias, right? If I look at the sigmoid, if the tan H, you can go through the pictures more carefully later, but then the same characteristic, same behavior remains. It's actually going to be a function a little bit of the weights and the bias, but not very much of the input, if I have the tan H. And the same thing with the ReLU. Things can blow up, things can die. The rate at which they're going to blow up or die depends on the weight And where they end up is going to depend a bit on the bias, but the input itself is not remembered, right? But what was the point of the recurrent network? You wanted to remember the input for a long time. Is it doing that? No. So these are not good, right? So this is, now, where does it, okay, I hit something over here. In this case, in this first figure, the recurrent weight matrix has a maximum eigenvalue of 1.1. Then you see the behavior. And the second one, it has a maximum eigenvalue of 0.9. And you'll notice that the two plots are not the same, right? So what this is telling us, what we find out is that to the far right, both the pictures in the left column are identical. Both the pictures in the right column are identical, but they are different for different values of the largest eigenvalue. So in other words, what is being remembered is a function of the bias and a function of the largest eigenvalue of the weight matrix, but not a function of the input. Is that making sense to everyone? Questions? Yeah.
Like this question, like in this case, like if you're experimenting, like how did you actually restrict the eigenvalue?
I can design my W any odd how, right? So in this case, I just created an a W with an eigenvalue of 1.1. That's it.
Actually, in practicality, when we're learning the network, it would be a difficult to constrain the eigenvalue.
It doesn't matter. It's either going to be greater than 1 or less than 1. It's very odd for it to be just 1, right? And so you're going to see this behavior. Yeah.
If I'm going to learn the network, then even the bias will change because of the input while I'm learning.
But once you have learned, the memory behavior of the network is only going to depend on the bias and the eigenvalues of the network. You should always think about it as what happens during inference time. Will it remember? No, it will not, right? So this is for, so you can actually perform formal stability analysis. And the math is slightly tedious. If any of you has done controls, you have probably done this analysis on your own. You pull up the Lyapunov exponents and check Roots criterion and things like that. What we will find, regardless of how you go about it, you're going to find this behavior. You have things like poles and zeros, depending on where they end up, where the system poles and zeros are. It's going to either blow up or it's going to die. And it's only going to, and this behavior depends only on the weight matrix and the bias and not on the input. Okay? So, all right, guys, apparently time's up. Can someone on Zoom answer the first question? Anybody on Zoom?
True.
Okay. So what is the answer to the first question?
The first three.
The first three. And what about the answer to the second question, Muna? Perfect, right? You guys got it. So how long an RNN can retain some memory of an input pattern depends on the weights of the recurrent layers, depends on the bias of the recurrent layers, and depends on the activation function of the recurrent layers. And what it remembers is going to be a function of the weights, the bias, and the activation function. It's really not a function of the input. Eventually, you're going to forget everything about the input, and all you remember is the system, not what the system is operating on. This is not the desired behavior, right? So recurrent networks retain information from the infinite past in principle. In practice, they tend to blow up or forget. They are not BIBO stable. If the largest eigenvalue of the recurrent weights matrix is greater than 1, then the network response may blow up. If it's less than 1, it may die. And the memory of the network also depends on the parameters and activation of the hidden units. So sigmoid activations saturate, and then the network becomes unable to retain new information. The same thing happens with TANH also, except it takes a little longer. And ReLU is going to blow up or die. It doesn't really matter. ReLU is really a very, very nasty thing to be doing to your poor recurrent neural network, right? So Given this, we end up with this situation. We started off claiming that recurrent networks are excellent for time series prediction and classification, for generating sequences. They can even simplify problems that are difficult for MLPs, but their memory behavior leaves something to be desired, right? Here's another problem. Some of you have alluded to this in the past classes, and you might have encountered this in your homeworks, this problem of vanishing gradients. Now, what exactly is the problem of vanishing gradients and why does it happen? Now, this is true not just for recurrent networks, it's true for any sufficiently deep network. The gradient of the loss with respect to the weights is going to be unstable. Why so? Consider any network of this kind. Now, a network is basically just a recurrent function, just a recursive function, right? It's a nested function. So the output y is W3 times the output of this layer, right? So I can say y is the final activation times Wn times Fn minus 1, which is the activation of this layer, which is applied to Wn minus 1 times Fn minus 2, which in turn is applied to Wn minus 3 times Fn minus 3 going all the way back. So is this equation making sense to you guys? You start with the input, you apply the first layer. I'm ignoring the biases, but assume they're there, right? So you start with the input, apply the first set of weights, then you apply an activation to it, then you apply the next set of weights, then you apply an activation to it, then you apply the next set of weights, then you apply an activation to it. The entire network is a nested function. The loss, the divergence is being computed on the output of the network, right? So the loss is now computed on y, therefore the loss is also a nested function. Everyone with me? Right. Okay, now look at the, I'm going to use some horrible notation over here. If I have some f of w of g of x, okay? If I want the derivative of f of w of g of x with respect to x, which is the innermost argument, that's going to be the derivative of f with respect to wgx times the derivative of wgx with respect to g of x times the derivative of g of x with respect to x. Written left to right because these are all vectors. My notation is bad. The nabla notation tends to be confusing, so I made this explicit, right? And so if I write this way, then if I let the argument of f just be represented as some z, then the derivative of f with respect to x is the derivative of f with respect to its argument z times the weight times the derivative of g with respect to x, right? So in general, if I write something of this kind, if I write d equals f1 of whatever w times f or fn times fn minus 1 times w of fn minus 2, pardon my chicken scrawl, the derivative of d with respect to any term over here, let me just call that x for some, for notation, just using some odd notation. This is going to be the derivative of fn with respect to its argument, right, times this w and times the derivative of fn minus 1 with respect to its argument times this next weight and so on. This was your derivative rule. Marlies, I promised you, right? You're just going through this whole thing. Any of you who didn't actually answer the derivative questions in the last class, you're basically chaining your computing derivatives. Backprop is just incremental multiplication to the right by the latest derivative. So you're going to be multiplying a Jacobian, then the Jacobian is multiplied by a weight matrix, then it's multiplied by a Jacobian, then it's multiplied by a weight matrix. That's what the math tells you, right? So everyone with me? And so I can write this. The derivative of the divergence with respect to the output of any kth layer is going to be the derivative of the divergence itself with respect to the output of the network times the derivative of the nth layer with respect to, when I just write nabla fn, its the derivative is with respect to the argument of fn, okay? The Jacobian times the weights wn times the Jacobian of the n minus 1th activation times the n minus 1th weight, and so on, all the way up to the kth layer, right? So all of the blue terms are matrices. A Jacobian is a matrix. A weight is a matrix. Every single term is a matrix, right? And you can see why this works. The derivative of the loss with respect to a column vector, which is the output of any layer, is going to be a row matrix, a row vector. The derivative of the loss with respect to the output of the network is also going to be a row vector. A row vector multiplying a matrix is a row vector. Multiplying a matrix is a row vector. It's going, all the dimensions will match up. But anyway, so this is the formula, right? Now let's consider these Jacobians. The behavior of what happens of the, Lakshak, you want to go out and sleep? There's coffee outside. Okay. Okay. So the behavior of this derivative depends on the Jacobians and the weight matrices. Let's look at the Jacobians. Now, what are the typical activation functions? Tan H, sigmoid, right? So if I think of a layer of neurons as having a layer of independent sigmoid activations, what is the Jacobian going to be? It's a diagonal matrix, correct? And each diagonal element is going to be the derivative of a single sigmoid. What is the largest value of the derivative of a sigmoid? 1/4, right? If I use a tan H activation, what is the largest value of the derivative of a tan H? 1. What is the largest value of the derivative of a ReLU? 1, right? So the derivative of this activation function is going to look something like this. Let's just say these Jacobians are diagonal matrices, correct? And now, if I actually take if I take a sigmoid, the derivative of the sigmoid with respect to, this is a tan H. The most commonly used activation function is a tan H. The green curve shows you the value of the derivative. In the best case, the derivative is 1. At other times, the derivative is always less than 1. The magnitude is less than 1, right? Okay. So what happens to a vector if I multiply it by a matrix, a diagonal matrix, whose diagonal entries are all less than 1? What happens to it? The vector will shrink, correct? So this means that over here, multiplying by the Jacobian is always a shrinking operation, right? If I go back to this equation for back propagation, every one of those circle terms shrinks my derivative. What remains? The weights matrix, right? Let's look at these weight matrix. Now a weight matrix, forget about what's on the board. Let me try to draw something. If I can find my chalk, otherwise we'll look at the board. Is there a chalk somewhere here? There's a bunch here. I lose chalks. I think I should leave chalks all over the place. Okay. Okay. So consider let's consider a unit circle, right? If I have a unit circle, a unit spheroid in general, and if I multiply every point on the circle by a matrix, what is the resulting picture going to look like? Pardon me? It'll become? It will become an ellipsoid, right? This is a linear transform. And so let's say that this length is 1. This, after transforming through some any matrix W, is going to end up becoming an ellipsoid. And the ellipsoid will have major and minor axes. Okay? This major axis is going to be the largest. What is that? Anybody know? Largest what? Eigenvector? Somebody want to improve on that? You're close. It's the largest singular vector, left singular vector corresponding to the largest singular value. Okay, So this over here is going to be sigma max. And this is, in this case, it's two-dimensional, so this is sigma min, right? So if I take a unit vector and multiply it by a matrix, the length of the vector is going to change, and it's going to change to a value that lies between the largest singular value and the smallest singular value. Right? Is that making sense to everybody? Not to you. You need to go get coffee. Okay. So, making sense? And specifically, corresponding to every left singular vector is a right singular vector, right? So what will happen is this delta D is going to expand along directions where the singular value is greater than 1, and it's going to contract along directions where the singular value is less than 1. And the majority of the singular values are going to be less than 1. If I generate a random weight matrix, the singular values are generally going to be less than 1. Okay? And so here's the behavior. Let's look at the whole thing in totality. Each block underlined by blue is a combination, a product of a Jacobian and a weight matrix. And this product is going to have some singular values and singular vectors. And as you keep multiplying this derivative delta nabla d with this term, as you go deeper and deeper backwards into the network, this derivative is going to elongate in a small number of directions corresponding to eigen singular values greater than 1. And it's going to shrink in every other direction. But the bad thing is that the directions along which the singular value for the first block are greater than 1 are not necessarily the same directions for the second block. So eventually, almost all of them will shrink. And so what is going to happen as you keep going backwards? We know the Jacobian is going to keep shrinking the vectors. And the W's are all not oriented with one another. So the vector will keep shrinking as it goes through, except for a small number of components which are going to blow up, right? And so you're going to get vanishing or exploding gradients. The gradient is going to vanish in the majority of directions, and it's going to explode in a direction where the singular values are consistently greater than 1 across all the layers. Yes.
Professor, didn't we say that singular values was always less than 1?
Not always. Singular values can be anything, right? The majority of the singular values are going to be less than 1. You just try this. Generate a random matrix and perform singular value decomposition on it and check the singular values.
Maybe I'm confusing it with our argument saying Jacobians diagonal entries are always less than or equal.
Oh, yes, that's for the Jacobians. For W's are not Jacobians.
Oh, okay, right.
In fact, if you have a rectangular weight matrix, which is not square, you have a large number of singular values that are exactly equal to 0. Right. So anyway, so you see what is happening. When you back propagate your derivatives through the network, as you keep going back through the network, the derivative is going to shrink along most directions, and there may be a tiny number of directions if you're lucky or unlucky, depending on how you look at it, where the derivative is simply going to blow up and explode. And so to give you an idea of how this works, here is an example from MNIST. This is a 19-layer MNIST model at initialization. Remember, at convergence, the derivatives are all expected to be 0, right? So let's look at what happens at initialization. That's when the derivatives are supposed to be largest. And the topmost, the picture here, these are all the neurons. These are the layers. All the layers have the same number of neurons in this particular example. And the color at any point shows the magnitude of the derivative of that particular neuron on a particular layer, right? And so these guys are the derivatives at the output layer. These are the derivatives of the second penultimate layer. These are the derivatives at the third layer from the output and so on. What do we see happening? As it goes down, the derivatives simply, they disappear, right? This is for an LU activation. This is for a ReLU activation. This is for a sigmoid activation. It doesn't matter. For the ELU activation, the derivatives last for up to 5 layers. But by the 5th layer, in every case, this is the derivatives have gone to 0. Right? They basically vanished because every layer shrinks the gradient. And so this is for tanh, right? Now this is for batch gradients. So we also looked at what happens for individual instances in your training set, also at initialization. So these are 9 pictures for ELU activations, and what do we see? After the 5th layer from the output, the derivatives are all gone. This is for, I have other pictures for tanh, pretty much for every activation. In fact, the ELU activation is the one that retains the derivatives longest, but it takes no more than 5 layers before the derivatives become vanishingly small. Now, they haven't all become vanishingly small. There's a small number of derivatives which have blown up to a very large value, except you can't see them, right? So what does this mean? It means that there's going to be just one single term in the entire input layer, first hidden layer, which governs the behavior of the entire network. If you perturb that a little bit, the output is going to change like crazy. The rest of them, you can perturb them as much as you want, the output really will not change. This is really not going to give you a very good network, and it's not going to help you train your network, right? So you have vanishing and exploding gradients, and this causes problems with training. So ELU activations maintain gradients longest. In all cases, they vanish after about 10 layers. And this happens for both the gradients across a batch and for individual instances. So going back, recurrent networks retain information from the infinite past in principle. In practice, they are poor at memorization. The hidden outputs can blow up, shrink. It depends on the eigenvalues of the recurrent weight matrix. The matrix memory is also a function of the activation of the hidden units. Deep networks also suffer from vanishing and exploding gradients. This has nothing to do with recurrent networks. Yes.
Is it possible that, like, what will be the dominant effect for vanishing gradient? Maybe the Jacobian or
The Jacobians are always going to be less than 1, right? So it will be the weights. Right. Now, and recurrent networks are just very deep networks. And so what this means is that it's impossible for you to learn how much perturbing a tiny input 10 times time steps ago perturbs the output now, because the gradients will simply vanish, right? Now, remember, stuff got forgotten even going forwards. And why did stuff get forgotten going forwards? Because all that got retained was the weights and the biases, right? The only condition under which it kept the memory was when the weights or the eigenvalue vectors of the weight matrix were identity, right? And so activations, it didn't matter which activation you gave it, it kind of blew up. So yeah. Which one? There's going to be one tiny dot somewhere, which is probably 1 pixel in the entire picture. So that's why you can't see it. Okay. Out of time. Someone on Zoom want to answer the first question? Zoom?
All of them.
All of them. Burhan, what about the second question? Same? All of them are true, right? You guys have, at least 2 of you are paying attention. I'm being mathematically precise. Anyway, so here is the problem we had. The problem we have is that things are not getting remembered. But then there are a great number of problems in life where you want things to be remembered, but you have a very specific manner of how you want things to be remembered. You want things to be remembered for as long as they are useful, and then you don't want to hold them on and hold on to them in memory because they're just a pain, right? So if you have something like, and the distance that you have to consider can be arbitrary. You have a fragment of a sentence over here, Jane had a quick lunch at the bistro, there in she. The word she occurs in the next sentence, but the fact that it's a she depends on the name being Jane and not Tom, right? So the length, you had to keep track of the fact that a female name was being referred to for as long as that person was going to remain the person who was being referred to by the pronoun, by any pronouns, right? So these are just other examples that come up. So I just gave you one toy example. So how do we solve this problem? Wait, first let me ask this. What is the cause of both of these problems, the vanishing gradients and the nasty, the really pathetic memory? Yeah, but you were getting halfway there, yeah. The activation functions, yeah, the activation functions were a pain. The moment you use activation functions, things blow up or die. What was the other thing that caused problems?
The nature of
The weights matrix, right? So long as you have a weights matrix, things are going to blow up or die. So what is our solution to this? Don't use them. Thank you, Lihan, he answered me, right? That is the answer. We are not going to use them. These guys, they were the pain, right? The activations and the weights matrix were the ones that caused the problems. Let's get rid of them. So instead, I want something of this kind, where whatever is being remembered is some initial value that I grabbed from the input, and then subsequently whether I want to continue remembering it or not depends on what else has come in. So I'd like to think about it in terms of, say, if you've got written a piece of code to analyze, to parse some C code. If you see an open parenthesis, you have to remember that the parenthesis was opened for as long as the parenthesis has not been closed. Once it's closed, you want to forget about it, right? And so you want to remember something, and then you want to keep it in memory till I get some trigger which says this is no longer relevant, I can close it. And so you really want, for every single item that must be remembered, you want a behavior of this kind where every subsequent input is analyzed, and depending on you found the trigger or not, you either continue to hold it in memory or get rid of it. So the memory now becomes dependent only on the inputs and what is already in memory, and not on any arbitrary weights or activations. So we want a mechanism of this kind. C of t is my memory, and it's going to go clean through with no weights. Every connection has basically just a diagonal identity matrix as its weights and no activations. The only way it's being modified is by multiplication through this gate, which looks at the current input and other relevant factors, the context, for instance, and then decides whether what must be in memory must be modified or not. Is this making sense? The rationale behind it and what we are doing, is that making sense to everybody? Okay. Questions? Yes, Abhishek.
Always know the trigger for.
No, we're going to learn all of this, right? But we are just going with the behavior that we want. Anybody, any other questions on Zoom? No, okay.
But if we get rid of the activation functions,
How will we introduce non-linearity in it?
You don't. Okay, so let's deal with it. Here's what the thing is going to look like. This guy is what we will call the constant error carousel. It's just going to keep things in memory. It doesn't modify it using any weights. It doesn't modify it using any activations. It only modifies it on the behaviors based on some gates which analyze the input to determine if this value must be changed or not. But then we need non-linearities. So how do we deal with non-linearities? You have the non-linear portion of the work is done by something else. So that can go into the actual non-linear work is done by other portions of that network. The C can go into some activation function that gives you the hidden non-linearly transformed hidden state. So this block is the constant error carousel. This is a term that you're going to run into. And what is the gate? So I've seen an open parenthesis. I want to determine whether the parenthesis must be closed or not. But then it's not enough for me to detect a closed parenthesis. I want to say how many times was the parenthesis opened? So you need to know what is in the memory also, right? Already in the memory. But then so you need to know not just what's in the input, but also what's in the memory and some additional context. Am I in a comment section or am I in actual code? So you want to look at a great deal of extra terms, including what's in memory, other stuff, and what's currently in the raw memory itself. All of these things must be taken into consideration to decide if the gate is going to modify the value or not. And so this structure is what we will call the long short-term memory neuron. The concept that's being encoded by the LSTM is basically the notion that we just discussed. Okay, questions? No? Okay. LSTMs explicitly latch information to prevent decay or blow up. And so I'm going to be using some notes which I borrowed from cola.github with various people. The pictures were nice, so when you see something good, why change it, right? Keep it. So here's how a standard recurrent network looks like. The recurrent value at any time is a function of the recurrent value at the previous time and the current input. And we like to think of each unit in terms of a cell, because this entire gating structure is complicated. What's happening inside the recurrent computation is fairly complex. So we can think of it as a cell. So a recurrent cell performs this operation. It reads in the recurrent value from the previous time and the current input to compute the current recurrent output, which can go into the subsequent layers upstream or into the future, right? This is going to be modified by this pretty hideous looking structure, but the structure is not as hideous as you would imagine. The logic that's encoded in it is fairly intuitive if you think about it, with a little bit of stuff. They like to throw in a few extras. So here you have two things. You have the, again, remember that we're using this side-on view. So every line represents a layer of neurons going into the page. Always remember that, right? This is your constant error carousel. What's in the constant error carousel is being modified based on patterns that you see in the input. So how is it? Now, when I see an open parenthesis, when I have a memory line which is keeping track of open curly braces, there are two things I can do. I can increment the number of curly braces if I find a new one, or I can decrement it, right? And now these two operations are different. In different contexts, I can say that whatever triggers the addition of a curly brace is different from what triggers the decrementing. So if I want two distinct operations, to have them both be additions becomes kind of redundant and less effective. So you want them to be two distinct operations. So here's what the network looks like. The basic unit is this remembered cell state. This is the constant error carousel, which has no weights. It has no activations. If some input is put into memory, it's going to remain there until otherwise, until something modifies it. And the modifications are going to be done by the lower portions of the network. So this CT is linear history carried by the constant error carousel. It's only affected by a gate, which is, or actually two gates, we will see. Now the first way of modifying it is this thing called a forget gate. So a forget gate is a simple sigmoidal unit which sort of scales the value that's currently in memory. So you've got you're remembering a whole bunch of curly braces, and now you've seen an open curly braces, and now you've seen a closed curly brace. So you want to decrement the count. You're going to decrement it using a multiplicative term. And obviously that's going to go between 0 and 1, right? Next, so this forget gate is a function of the previous hidden state, HT, and the current input. And it multiplies what's in the raw memory, the constant error carousel. But then you want something else. You want to maybe increment it too. So now we want to be detecting patterns, right? You want to detect if you've seen another open curly brace, or if you've seen another closed curly brace. So you need a pattern detector. The TAN-H there is a pattern detector. It's detecting if there are other things in the input that must be used to modify the input. But then they like to gate it because, again, using my coding example, I might find another closed curly brace or open curly brace, but it may occur in a comment line. And so you need to say, is this really relevant? Must this modify my output? And so you have the TAN-H over here, which operates on an affine combination of the previous hidden state and the current input. And this is a pattern detector, which computes the pattern C tilde. And this is what's called an input gate, which determines whether what has been detected is relevant or not, and whether it must be used to modify what's in ROM memory. And so the final modification to ROM memory is a combination of two operations. It forgets multiplicatively based on what the forget gate has found, and it increments additively based on what the input pattern detector after waiting by the input gate has found. Now, there's the final bit. Everything, the hidden state itself is non-linearly transformed, right? The horizontal constant error carousel is not modified in any non-linear way, except by something that's been read off the input. And so that, in order to actually perform hidden state operations on it, you put it through a tanh compression, and so now you get your nonlinearity. And then here's the final bit. Now, because we are in the business of making the network complicated and throwing lots of gates, let's throw in yet another gate, because why not? And so this output is multiplied by what is called an output gate, which nominally determines whether what's in the nonlinearly transformed memory must be passed through as is, or whether it must be compressed or expanded. So now the non-linearly compressed memory state actually carries information about the previous state, but maybe there's some loss of information because it's gated. So they found that you can just add a direct connection from the raw memory itself, and that improves the performance. They call it the peephole connection, nothing special about it. But then the entire collection of operations is shown by this figure over here. You have the constant error carousel going through. At each time, what's in the raw memory, the previous hidden state, and the input is operated on by this forget gate, which multiplicatively modifies the raw memory. And then, and so this would only decrement it, right? Subsequently, you have this pattern detector, which tries to detect if there are any more interesting patterns. And its output is modified by the forget gate, which determines the relevance of this pattern that has been discovered, and that's added to the what's in raw memory. And this guy is finally sort of modified by this non-linearity, which is the tanh, and the output of the tanh is again modified by this output gate before it's passed on as the hidden state. Now, there's one key difference here between these three gates. These two gates operate on the raw memory before it was modified. The output gate operates on the raw memory after it was modified. So that's the connections into these gates come from different places. Now, this is just engineering. There's no why to it. This is how it was done. Now, yeah. Okay, time's up. Sumesh, can you answer the question? True? Which are the ones that are true? Anyone else? All of them. Okay, all of them are true. You lady at the back, can you shut your laptop? Thank you. So here are the set of computations. Now, I've just got some arithmetic over here. This is only meant for your reference. We are, and I'll quickly go over them just because there's some order of computation that you have to take into consideration, which is that you first compute the forget gate, then you compute the input gate, and then you compute this pattern detector. And only when all three are computed can you update your what's in raw memory. Then you need what's in raw memory to compute this output gate and this nonlinearity, and those two are multiplied to get the final output. So there's a sequence. It looks complicated, but you can actually sequentialize the whole thing. I have some pseudocode. I'll skip it. Now, training this network is identical to training a recurrent network with one small modification. It's hard. So why is it hard? here are two continuous cells, right? And let me try to figure out what are all the derivatives that manners in which I can have to pass derivatives back to compute the derivative of the loss with respect to CT. Here's one path. It comes from HT, right? Then here's another path. It comes through the second line. Then here's a third path. It comes through this third line. Then here's a fourth path that comes through this fourth line. And was there more? You get the idea, right? I don't know about you, but I don't want to do this math. So same thing with, if I want the derivative with respect to HT, I can keep going on, right? So when you get to such ugly things, then what do? Auto differentiation. But then if you didn't have an auto def, what do? Cry. We did this with CNNs. What was the operation we did? You look at it through code, right? And so the simple thing is, so I'm not going to explicitly derive the derivatives with respect to any of these parameters, let alone the weights, but there's a very nice handout on the course page called How to Compute a Derivative. I strongly, strongly recommend that you take a look at it. I won't go over it through the lecture, but if you go through the How to Compute a Derivative handout, it makes this thing trivially simple. And if you actually follow it, you should be able to compute the derivative for pretty much any function that is computable. Okay? So I'm trusting you guys to do the right thing, but because I don't trust you enough, I also give it to you as a homework. That way you have to do it. But here's the general mechanism. If I write out the equations top to bottom, I can just write down all of the formulae, and then I can compute the derivatives going back one step at a time. There's a lot of code, but the thing will just work, okay? So one final bit. Why is the entire thing so complicated? But before that, okay, I just want to point out one small thing, that when you compute the derivative, when you're going backwards, you're going to get derivatives coming in through HT, CT, and ZT. And the output must compute derivatives for these three guys coming out. This derivative will go down to the lower layer, and you're also going to get derivatives for all the weights inside the network. So make sure that you get all of those. Now, if the LSTM seems unnecessarily complex, it actually is. The basic concept can be retained while simplifying the unit a whole lot. And so various people have tried various things, and generally with some success. One of the most successful ones is this thing called the gated recurrent unit. Now, it's going to address some of the questions of why this much complexity. This looks much simpler than your LSTM, right? What changed? I have a forget gate and I have an input gate. This doesn't make sense, right? If something is modifying the memory, then it's not. So if something is decrementing memory, it's not going to be incrementing it. So the same operation, the same symbol cannot have the memory both decrease and increase. Meaning what is happening at forgetting is related to what's happening at the input. So they combine the two gates. The forget gate is 1 minus the input gate. Problem solved, right? So you get a single unit. And then similarly, we were retaining two different versions of the recurrent state. You had the raw memory, then you had the compressed version of the raw memory. Both of them are the same thing. Why retain two of them? So you just have one single go through constant error carousel line. And when you actually want to operate on it, then at the time of operation, before you use it, you actually put it through a nonlinear compression. You can gate it. There's a gate over here, which modifies the value and then puts it through a nonlinear compression. So you get rid of some of the operations in the process. There are other ways of modifying the LSTM cells, so long as you know what the underlying concept is. The underlying concept being that what's in memory must go through unchanged unless modified by gates which explicitly operate on patterns detected in the input. If you can hold on to that concept, you can modify the structure and simplify it, and maybe things will work. But we're way past the time where you can write new papers about it because they've squeezed it down. But again, You can use this LSTM unit on all kinds of architectures. So each one of those green blocks now is going to be an entire LSTM cell. You can also use it in a bidirectional network. Each of those green blocks is now going to be an LSTM cell. And so on time, I skipped a bunch of stuff, but it's in the slides. LSTMs, recurrent networks are poor at memorization. The memory can explode or vanish depending on the weights and activation. They also suffer from a vanishing gradient problem during training. The loss at any time cannot affect parameter updates in the too distant past. So for example, seeing a closed bracket cannot affect its ability to predict an open bracket if that open bracket happened too many time instants ago, right? So LSTMs are an alternative formalism where memory is made more directly dependent on the input rather than network parameters or network structure. And this is done through a constant error carousel, which has no weights or no activation. So you got rid of all of the nasty components which actually have a bad influence on memory behavior. And these things do not suffer from a vanishing gradient problem because of the latching mechanism. But it turns out that they do have an exploding gradient problem because things keep getting accumulated. And so you have some issues. I'll let you to figure this out and deal with it in your homework. We're going to move on in the next class. Any questions? Thank you.